Imagine you're an investigator, right? You're walking to this massive corporate crime scene, and you find the smoking gun. It is this sleek, incredibly fast, solid-state drive sitting right there on the suspect's desk.
Best feeling in the world, initially.
Exactly. You know it contains the exact financial ledgers needed to prove a massive multi-million-dollar fraud case. But here is the terrifying part. The very act of that drive, just sitting there, powered on, means it is actively destroying its own deleted evidence, byte by byte.
Yep, just chewing it up.
It is altering its digital fingerprint right before your eyes. So, welcome to the invisible ticking clock of modern data acquisition.
It really is a ticking clock. I mean, if you don't understand the physical architecture of that drive and, how to actually stop its automated maintenance cycles, your evidence is permanently gone before your hands even touch the keyboard.
To you, the driven student at Tarleton State University's Dr. Sam Pack College of Business, or honestly, anyone tuning in who is serious about their future, welcome to this deep dive. We're going to teach you exactly how to stop that ticking clock.
Which is a pretty vital skill.
Absolutely. Before we do, make sure to hit subscribe right now, like, share, follow, comment. We're giving you the insider tools to stand out and position yourself for a brilliantly successful career in MIS, CIS, or IT. And don't forget to check the description below for links to additional resources you will find incredibly valuable.
Taking ownership of your career growth really requires a lifelong learning mindset. And understanding the actual mechanics of how data is preserved, that is a massive competitive advantage in the business world.
Last week, we explored Chapter 3, Unpacking the Investigator's Laboratory and Digital Forensics Tools. Today, we are taking our next critical step into Chapter 4, which is data acquisition.
Right.
This is based on the Guide to Computer Forensics and Investigations, the 2025 edition by Nelson, Stewart, Phillips, and Wilson. And for those tracking the curriculum, this is our 4th deep dive out of 15 in this series.
So let's lay out our mission for today. When we talk about data acquisition in, say, an enterprise or a legal context, we aren't talking about dragging and dropping a few folders onto a thumb drive.
No, definitely not.
Right. Data acquisition is the meticulous, scientifically rigorous preservation of digital evidence. You're creating a forensically sound, bit-by-bit replica of the original media.
Which is a huge deal.
It is. For a business student or a future IT director, understanding this methodology is literally the difference between saving your company in a massive e-discovery lawsuit and losing a case entirely along with your job, probably on a completely preventable technicality.
Because opposing lawyers will absolutely tear your methodology apart if they find a single flaw. So, to understand how we save that evidence before the S&D destroys it, we have to talk about where we put the data once we extract it.
The storage formats.
Right. When a forensics tool collects data, it stores it as an image file. Based on our sources, there are essentially 2 paths you can take here. You've got open source formats, or you have proprietary formats. Let's look at the open source side first, starting with the raw format.
Well, raw format is it's the oldest and most fundamental storage method. Its primary advantage is resilience and speed.
Because it just blasts through errors, right?
Exactly. When you copy a drive in raw format, the software just completely ignores minor data read errors on the source drive. So if the acquisition tool hits a physically damaged sector on the suspect's hard drive, it doesn't freeze or crash the software.
Which is nice.
Yeah, it just notes the error and keeps plowing forward. And because of its simplicity, almost every single computer forensics tool on the market can read a raw format file.
But there is a massive logistical catch with raw format. It requires a true one-to-one storage match.
That is the glaring disadvantage. A raw format image requires exactly as much storage space as the original disk, regardless of how much data is actually on it.
Let's put this in a business context for the listeners. Imagine you have a 10 terabyte corporate server. The suspect only have like 50 megabytes of stolen PDF files saved on that server. If you run a raw acquisition, your resulting image file will be exactly 10 terabytes.
Yep.
It copies the 50 megabytes of data and 9.99 terabytes of absolute, completely blank space.
Which is just a nightmare.
It seems completely unmanageable for modern businesses. I mean, if I am an IT manager at a mid-sized corporation looking at my budget, I might be tempted to default to raw format, so I never have to worry about software licensing or vendor lock-in.
Yeah.
I want anyone to be able to read my evidence. Why wouldn't I just do that?
Because of scalability. I mean, your instinct to avoid vendor lock-in is smart, but modern enterprise data doesn't exist on 500 gigabyte hard drives anymore. We are talking about server farms with hundreds of terabytes of storage.
Right.
If you try to do a raw acquisition of an entire enterprise environment, you would need to purchase an equal amount of empty, sterilized storage just to hold the raw image. The hardware cost and the physical logistics of moving that much storage are completely unscalable.
Which naturally leads us to the second open source option, which is Advanced Forensic Format, or AFF.
Yeah, AFF was designed by Dr. Simpson Garfinkel specifically to solve that exact scalability problem of the raw format. Since it's open source, digital forensics vendors have no implementation restrictions.
No licensing fees.
Exactly. The brilliant part of AFF is that it provides the option for highly efficient compressed image files. It mathematically shrinks that 9.99 terabytes of blank space down so your final image file is vastly smaller, saving you massive amounts of storage budget.
And it also handles the metadata. The data about the data, like creation dates and system architecture, really intelligently.
It does. It has dedicated internal architecture for metadata. You'll actually see file extensions like .afd for the segmented image files and .afm specifically for the AFF metadata.
Oh, interesting.
Yeah, it's extensible, it works seamlessly across Windows, Linux, Mac OS, and critically, it has internal consistency checks. This means it uses mathematical algorithms to prove to a judge that the file hasn't been tampered with since the moment it was acquired.
So those are our open source tools. Yeah. Then we have proprietary formats. These are created by commercial forensics software vendors to work exclusively with their own high-end analysis tools.
Right, and proprietary formats offer some incredibly powerful, streamlined features. They provide heavy compression algorithms. They can easily split a massive server image into smaller, segmented files so you can distribute them across multiple smaller target drives.
That's super useful.
It is. And they integrate the metadata seamlessly into the core image file so nothing gets separated.
Think of these storage formats, like physical moving and storage solutions. Raw format is like throwing all the evidence into a giant standard cardboard box. It's universally understood, anyone knows how to open it, but if you have a single couch, you still have to buy a box the size of an entire house to fit the room the couch came from.
That's a great way to put it.
And then AFF is like a high-tech, expandable smart box. It mathematically shrinks to fit only the contents, it categorizes everything, and it's open source, so anyone can learn how to open it. Proprietary formats, though, are like a locked steel vault. Super secure, incredibly space efficient, but only the vault manufacturer holds the key.
And that locked vault perfectly illustrates the major risk, which is vendor lock-in. If you acquire a massive corporate image using one vendor's proprietary format, and then say your consulting firm switches software providers next year,
You're stuck.
you might have a complete inability to share or open that older image with your new tools. You are entirely at the mercy of the software vendor's ecosystem.
So we have the box, but we can't just shove the server in blindly. We need a strategic action plan to extract the evidence safely.
Planning is everything in this field. I mean, spending time preparing an acquisition gives you the opportunity to anticipate technical roadblocks before you are standing in a hostile suspect's office sweating through your shirt.
Yeah, that's not the time to be figuring things out.
Definitely not. A general acquisition action plan identifies the exact hardware resources required, creates a step-by-step outline of the execution, details the chain of custody for preservation, and strictly defines the physical and network security of the evidence before, during, and after the acquisition.
And practically speaking, the sources point out you have to be prepared for a very long stay at the remote site. Data transfer takes time. When we look at the actual acquisition environment, we're dealing with two main scenarios, right? Static acquisitions and live acquisitions.
Exactly. So a static acquisition is the traditional gold standard. The device is physically powered off, it is hardware write protected, and the data is completely resting.
Frozen in time.
Yes. Because the environment is frozen, static acquisitions are entirely repeatable. You can take the image today, and 10 years from now, a defense expert can take another image of that protected drive, and the mathematical hashes will be utterly identical.
But in the real business world, sometimes you can't just yank the power cord out of the wall.
That is where live acquisitions come in. This is deployed when a suspect computer like a critical company email server routing thousands of messages a minute simply cannot be shut down without causing catastrophic financial damage to the business.
You can't just bankrupt a company to get an image.
Right. But the inherent risk here is that captured data might be altered during the acquisition because the system is active. The operating system is constantly running background processes, altering log files, shuffling RAM. Because the data is moving, A live acquisition is not repeatable.
So if you image a live server at 1:00 p.m. and again at 1:05 p.m.
The images will be fundamentally different.
Wow. Okay, so whether we are in a static or live environment, we have four distinct methods for actually collecting the data. The first is creating a physical disk-to-image file.
Which creates a bit-for-bit replication of the original drive, capturing every single 1 and 0, including the empty space and deleted files. This is the most common method and provides the highest level of forensic fidelity.
The second is a physical disk-to-disk copy.
Right, and you deploy this when a disk-to-image file isn't physically possible. Often this happens when you are dealing with very specific legacy hardware or a hard drive that is physically failing and making those awful clicking noises.
Ugh, the click of death.
Exactly. You are literally cloning the geometry of one physical drive directly onto another identical physical drive just to save the data before the mechanical arm snaps.
The third method is logical acquisition, and this is where the business use cases really shine.
A logical acquisition captures only specific files of interest to the case, rather than the entire drive. Imagine a massive civil litigation involving e-discovery. The legal team is looking for a specific chain of emails that proves a breach of contract.
Right.
You do not image the entire 50-terabyte corporate network. You perform a logical acquisition of just the specific Microsoft Outlook.pst files. It saves weeks of transfer time and millions of dollars in storage and analysis fees.
The fourth method is sparse acquisition. How does that differ?
Sparse acquisition is incredibly targeted. It's similar to a logical acquisition because you are extracting specific active files of interest. But crucially, it also drops down into the drive's unallocated space, the empty areas where deleted files go, and collects fragments of data that might be related.
Let's frame this for the business student. Say you are investigating a corporate spy who you suspect is downloading proprietary client lists, emailing them to a competitor, and then deleting the local files to cover their tracks.
Classic scenario.
Yeah. A logical acquisition might just grab the active documents folder and completely miss the evidence because the spy deleted the files. But a sparse acquisition grabs the active documents and then systematically combs through the unallocated space to reconstruct those deleted fragments of the client list. It's an incredibly powerful tool when you suspect intentional data destruction.
It is, but you generally only use logical or sparse methods when your time is heavily restricted, or the source disk is simply too massive to copy entirely. You constantly have to weigh the size of the suspect disk, the legal scope of your search warrant or subpoena, and the geographical location of the servers.
Let's touch on compression again. We discussed using AFF, or proprietary formats, to mathematically compress the blank space and save storage. This is called lossless compression, meaning the data isn't degraded when compressed, unlike, say, heavily compressed JPEG images where the picture gets blurry.
Right.
But if I'm a defense attorney cross-examining you on the stand, I'm going to point at you and say, you ran my client's data through a compression algorithm. How can the jury trust that the software didn't accidentally alter a single comma in my client's financial records?
Oh, opposing counsel will absolutely attack the integrity of the compression. Fortunately, the forensic methodology gives us a bulletproof 4-step hash test to mathematically prove the compression is truly lossless.
Walk us through those 4 steps.
Step 1. Before you compress anything, you run a cryptographic hash algorithm like SHA-256 on the original file. This generates a unique 256-bit string of characters that represents the exact contents of that file.
Okay, got it.
Step 2. You run your compression software on the file. Step 3. You uncompress the new file and save it to an entirely isolated target drive. And step 4, you run the exact same SHA-256 algorithm on the newly uncompressed file.
And compare the 2 strings.
Exactly. If the compression software worked perfectly without degrading a single bit of data, both versions of the file will generate the exact same complex hash value. It is mathematical proof of integrity, and it shuts down the defense attorney's argument immediately.
Even if your strategic plan is flawless and your compression is mathematically verified, you are still going to hit a wall when it comes to time.
Yeah.
Data transfer physics can't be ignored. Calculating acquisition time isn't just a blind guess, it is a strict mathematical equation.
The time it takes for data to migrate from the suspect's hard drive to your sterilized target drive is governed by the slowest bottleneck in your hardware chain. First, you have to find the source drive's maximum read speed, like how fast can the suspect's drive physically spit data out. Second, you look at the controller interface. Are you bottlenecked by an outdated USB 2.0 connection, or are you utilizing a high-bandwidth internal SATA connection? Third, you evaluate your target drive's maximum write speed. How fast can your drive absorb the incoming ones and zeros?
The textbook also highlights variables that investigators constantly overlook, like the CPU clock speed of the laptop managing the transfer, the bus architecture on the motherboard, and, perhaps the most frustrating, the physical quality of your cables.
Oh, cables will ruin you.
A cheap internally frayed cable will drop packets and throttle your entire operation down to a crawl.
Absolutely. To calculate your estimated time on site, you identify the absolute slowest device's data transfer rate in your chain. Then you simply divide the total size of the suspect drive by that specific rate. That will give you a remarkably accurate timeline.
So you do the math, and you realize you are going to be sitting in a hostile corporate office for 14 hours waiting for a progress bar. You desperately need a contingency plan. Because what happens if, at hour 13, your imaging software hits a memory leak and crashes?
That nightmare scenario is exactly why the standard practice, the absolute non-negotiable rule in digital forensics, is that investigators must make at least 2 separate images of the critical digital evidence.
And it is vital to note we aren't just running the same software program twice.
Correct. Your first copy should be acquired using one specific tool, and your second copy should be acquired using an entirely different tool from a different developer. We do this to mitigate MTTF mean time to failure.
Because everything breaks eventually.
Exactly. Every physical storage drive has a mechanical lifespan and will eventually fail. And every software program, no matter how expensive, contains anomalies or undiscovered bugs.
Relying on a single forensic tool in a multi-million-dollar corporate espionage case is like having only one set of accounting ledgers for a Fortune 500 company during a massive IRS audit.
Yeah.
If that specific ledger gets corrupted by a spilled cup of coffee or has a fundamental formula error in the spreadsheet, the entire company goes under.
Yeah, you're done.
2 independent tools give you independent verification. If one software tool encounters a bizarre architecture error it can't handle and corrupts the image, you have a completely separate, independently verified backup.
Beyond hardware degradation and software bugs, your contingency plan has to account for deliberate architectural hurdles built into the drives themselves. A prime example is the host protected area, or HPA.
What exactly is the HPA and why does it matter?
So the HPA is a specific partitioned area of a disk drive that is reserved by the manufacturer for booting utilities, diagnostic programs, and system recovery files. The key feature of the HPA is that the computer's standard operating system cannot see it.
Wait, really? It's just totally hidden?
Entirely invisible to the user and to standard file browsers. Because it operates in the shadows, sophisticated bad actors and corporate spies actively use the HPA to hide stolen intellectual property or malicious rootkits. If you use a basic non-forensic copying tool, it will completely bypass the HPA, meaning you leave the most critical evidence behind. You have to ensure your forensic imaging tool is explicitly designed to recognize and extract data from the host protected area.
Wow. Then we have the ultimate contingency hurdle, whole disk encryption. We are talking about enterprise-grade tools like Windows BitLocker. BitLocker performs a sector-by-sector encryption of the entire drive. Every single sector is mathematically scrambled into gibberish, making it totally unreadable when you copy it with a standard static acquisition method.
It is a massive investigative roadblock. Executing a static acquisition on a whole disk encrypted drive currently involves running a decryption sequence on the drive first.
Wait, hold on. If the cardinal rule of digital forensics is never alter the original drive, wouldn't running active decryption software directly on the suspect's computer completely violate that rule?
It is a completely logical concern, but we have to look at the mechanics of what decryption actually does. Decrypting a drive does not alter the actual allocated files or overwrite the unallocated data.
Yeah.
It simply provides the cryptographic key to unlock the mathematical scrambling so the underlying data can be read by your imaging tool. The real threat to the investigation isn't the decryption process altering the data. The real threat is that decrypting the drive requires the suspect's cooperation to provide the password or the recovery key.
And if they don't cooperate?
If the suspect refuses to cooperate or the corporate IT department conveniently lost the enterprise recovery keys, brute forcing that encryption is phenomenally difficult, computationally expensive, and sometimes mathematically impossible.
So we've established that we have to make 2 copies, deal with hidden partitions, and navigate encryption. But we have a glaring operational problem. If I take this suspect's drive and simply plug it into my standard Windows laptop to make that copy, Windows instantly starts altering the evidence behind the scenes. How do we build a bridge between the suspect drive and our computer without contaminating the crime scene? This brings us to the tech arsenal.
The foundational rule of the tech arsenal is understanding that accessing a suspect disk drive directly via a normal commercial operating system is incredibly destructive.
Just totally ruins it.
Yes. The second you plug a suspect's USB drive into your everyday Windows laptop just to look around, the Windows OS immediately begins writing hidden system files to that USB drive. It automatically updates last access timestamps, it creates hidden recycling bin folders, and it irreversibly alters the digital footprint of the evidence.
How do we stop the OS from doing what it was programmed to do?
You must sever that write capability using a well-tested write-blocking hardware device or a highly specialized software application. A hardware write blocker is a physical bridge that sits between the suspect drive and your computer. It intercepts the data flow at the hardware level.
Like a one-way street.
Exactly. It allows data to flow outward from the suspect drive into your computer, but it acts as an impenetrable brick wall, physically dropping the write-enable signal so absolutely no data from your computer can flow backward to alter the suspect drive. While some international jurisdictions are still catching up on the legal acceptance of write-blocking devices, in almost all U.S. enterprise and legal environments, they are non-negotiable.
Hardware write blockers are fantastic, but what if you don't have one physically with you? There are entire operating environments designed specifically for safe acquisitions. Enter the Linux Live CDs, DVDs, and USB distributions.
Yes, several Linux distributions are built as ISO images, which is basically a compressed snapshot of a full operating system that can be written to a bootable USB drive. You plug this USB into the powered-off suspect computer, you command the computer's motherboard to boot from your USB instead of its internal hard drive, and suddenly you are running a secure, forensic-grade operating system entirely within the computer's volatile RAM.
And the genius of this approach is that well-designed forensic Linux distributions are hard-coded, specifically not to mount the suspect's internal drives automatically. If they do mount them, they force them strictly into a read-only state.
Exactly. But it's important to note that not all Linux is forensic Linux. Your standard Ubuntu recovery disk isn't designed for strict evidence preservation. You need purpose-built distributions like Kane, Knoppix, the SANS Investigative Forensic Toolkit, commonly known as SIFT and Kali Linux.
Let's focus on Kali Linux. In the IT world, Kali is famous as the premier tool for penetration testing and ethical hacking, but its forensic capabilities are incredibly robust.
Kali Linux comes in a variety of configurations, scaling from a lightweight 856 megabyte version all the way up to full-featured builds for 64-bit systems, ARM architectures, Apple M1 chips, virtual machines. When you boot Kali Linux live from your USB, you are presented with a specific boot menu. One of the primary options is Forensic Mode.
And that's the magic button.
It is a critical feature. Forensic Mode explicitly alters the Linux kernel boot parameters to completely skip the automated mounting of any physical drives connected to the motherboard. It touches absolutely nothing, guaranteeing no accidental writes to the evidence. Furthermore, it comes pre-packaged with the Linux version of Autopsy, which is an exceptionally powerful forensic analysis suite.
But what if you are consulting for a massive corporation that is deeply integrated into a Windows environment? A Linux interface might not be able to natively parse the highly specific proprietary Windows registry files you need to extract. That brings us to Mini-WinTFE.
Mini-WinTFE is a highly specialized tool for those exact scenarios. It enables an investigator to custom build a Windows forensic boot environment on a USB drive. It takes the standard Windows pre-installation environment, which is normally used to install Windows on a blank PC, and modifies its core registry.
Sneaky.
Very. When you boot the suspect computer using Mini-WinTFE, the modified registry dictates that all connected drives are automatically mounted strictly as read-only.
For a business student aiming for IT management, the value of Mini-WinTFE is massive. Give you home field advantage. You get to survey Windows-specific OS files, and you can access the suspect's Windows registry files natively, using Windows architecture without ever altering the source files. You maintain total data integrity while working in an environment tailored perfectly for Windows artifacts. You simply have to remember to connect a secondary, large-capacity target USB drive to the computer before booting Mini-WinTFE. That gives you a place to save the extracted evidence. Once the environment is booted, you use a specific command to manually switch only your target USB drive into read-write mode, while the suspect drive remains safely locked in read-only.
While we are discussing the tech arsenal, we have to highlight the actual acquisition software, specifically Xtero's FTK Imager. This tool is a foundational staple in the digital forensics industry. It can execute a flawless bit-by-bit physical acquisition, or it can be dialed in to copy only logically selected files.
And it does something special while it copies, right?
Yes, what makes FTK Imager exceptionally efficient is that as it streams the data from the suspect drive, it is simultaneously calculating the complex MD5 and SHA1 mathematical hashes. The moment the copy is finished, it immediately verifies the newly created image file against those hashes to ensure absolute mathematical perfection.
It performs the validation natively while it manages the copy. That saves hours of processing time.
It's highly optimized. It easily fits on a standard flash drive and can even be integrated directly into your Mini-WinFE boot drive. But you must remember the golden rule. Because FTK Imager is a software application, it inherently requires a hardware write blocker, or it must be run from a forensics-enabled boot media like Mini-WinFE to perform a safe static acquisition without letting the host OS contaminate the drive.
We have our write blockers, we have Kali Linux and Mini-WinF. But before you plug in your flashy forensic USB and start extracting data, you need a sterile place to put the data you are about to extract. Let's move into the operating room and discuss target drives and evidence collection.
The single most critical foundational task in conducting a digital forensics examination is the pristine collection and preservation of evidence. If you contaminate the target drive, the brilliance of your extraction tools doesn't matter at all.
The textbook outlines a strict three-step protocol for preparing a target drive. Step 1. You must use only brand new or freshly wiped and forensically formatted drives. Step 2. You must meticulously document the media information in your physical or digital journal. Step 3. You securely preserve the forensic media so it remains uncontaminated and ready for deployment.
Let's focus on step 1, wiping. A lot of entry-level IT folks think they can just drag old files to the recycling bin, hit empty, and call the drive clean.
Yeah, that is a disastrous misconception.
It really is. When you delete a file in Windows, the operating system doesn't actually erase the data. It simply deletes the master file table pointer that tells the computer where the file is.
It essentially rips the chapter out of the table of contents, but the text of the chapter is still fully written on the pages of the hard drive.
Exactly. To prepare a forensic target drive, you have to wipe it, which means actively overwriting every single sector of the drive with zeros. If you are operating in the Windows command line, you can format a drive using the format command combined with a /p:/NTH switch, which forcefully overwrites every sector. Alternatively, you can use the diskpart utility and execute the clean all function, which performs the exact same zeroing process.
The sources are incredibly strict about the legal dangers of data commingling. If you just quickly erase a drive instead of zeroing it out, opposing counsel can legally demand to inspect your target drive during discovery. If their forensics expert runs an unallocated space scan and finds remnants of old case files, perhaps confidential employee health records from an entirely different corporate lawsuit you worked on last year on your target drive, it completely discredits your professional methodology.
The judge will question everything you submit from that point forward.
Wiping the target drive is exactly like a surgeon sterilizing the operating table before a major procedure. If the opposing lawyers find a bloody Band-Aid from a previous surgery stuck to the bottom of your operating table, your entire case is dead on arrival. No jury will ever trust your cleanliness or your results again.
Yeah, it's a huge liability. Once the drive is forensically wiped, you must format it to a compatible file system. The industry standard rule of thumb is if your target drive is over 32 gigabytes and you are operating primarily in a Windows forensic environment, you should format it to the NTFS file system to handle massive file sizes.
Right.
Then you meticulously document everything in your chain of custody journal. The type of media, the manufacturer, the exact model, the physical serial number, its total storage capacity, its intended purpose, the volume of partitions, and the final physical disposition of the media in your evidence locker.
The target drive is sterile. The journal is updated. Now we approach the suspect's computer. We established earlier that we want a boot from our forensic USB, not the suspect's internal hard drive. To achieve this, investigators must deeply understand how to access and modify the computer's fundamental boot sequence at the motherboard level.
This requires a solid grasp of hardware architecture. A standard computer stores its baseline system configuration, its date, and its time information in a volatile memory chip called the CMS, the complementary metal oxide semiconductor, which is kept alive by a small watch battery on the motherboard, even when the computer is unplugged.
So to intercept the computer before it loads its operating system, you have to access the CMOS or BIOS setup menu within the first few seconds of powering the machine on.
You do.
Every IT professional knows this moment. It is that panicked 3-second window where you hit the power button and just start frantically mashing the F2 or F12 or delete key, praying you trigger the hardware interrupt before the Windows logo appears on the screen.
Because if that Windows logo appears, you have failed. The system has initiated the boot sequence from the suspect drive, background processes have launched, timestamps have been updated, and the digital crime scene is officially contaminated.
Game over.
Pretty much. Once you successfully intercept the boot and enter that blue or gray setup screen, you navigate to the boot priority sequence and force the motherboard to look at your forensic USB drive first. However, you must understand the underlying architecture you are navigating. On older x86 systems, the hard disks use a master boot record, or MBR, and you are interfacing with a traditional BIOS and CMOS menu.
But on modern x64 enterprise systems, the disks utilize a GID partition table, or GPT, and you are dealing with a much more complex extensible firmware interface, or EFI, or the Unified Extensible Firmware Interface, UEFI.
You have to be fluent in navigating all of these firmware interfaces to ensure a secure forensic boot across different generations of corporate hardware.
There is a fantastic pro tip from the textbook regarding this process. Always memorize the exact manufacturer brand and the precise storage size of your forensic USB drive and your target drive before you start. When you are staring at a cryptic, text-only UEFI boot menu, seeing a list of generic drive names can be terrifying. Knowing definitively that your forensic boot OS is on the Kingston 32GD and your sterilized target drive is the Western Digital 4TB makes it significantly easier to select the correct boot device and avoid accidentally booting the suspect's internal drive.
Eliminating ambiguity is key to avoiding catastrophic mistakes. Now let's assume you have booted safely into your forensic environment and you are executing a logical acquisition. You are bypassing the full physical image to collect only specific directories. The textbook highlights several powerful command line tools for this exact task. In a DOS or Windows command line environment, you have the excacopy command.
Oh, excacopy is an absolute classic for moving data.
It is deeply reliable. While the basic copy command works for simple tasks, Desacopy possesses specific switches designed for complex directory trees. For example, if you append the switch /thesaurus to your command, Desacopy will recursively copy all folders that contain actual data, but it will smartly ignore completely empty folders, which dramatically speeds up your transfer times in deeply nested corporate directories.
But when you are dealing with massive, high-stakes e-discovery cases, the textbook steers us away from Desacopy and points us directly to Robocopy.
Robocopy, which stands for Robust File Copy, is the undisputed heavy lifter for enterprise logical acquisitions. It is engineered specifically for scenarios where only the raw data files are required, but metadata and structural integrity must be maintained. The power of Robocopy lies in its granular command line switches.
Like what?
For instance, if you execute Robocopy /avefp, the software will explicitly display and record the full absolute path name of every single file it copies. In a corporate lawsuit, proving exactly where a specific spreadsheet was located on a suspect's deeply nested network drive is just as important as the spreadsheet itself.
Let's look at the business impact of that. If you are an IT manager executing a collection for legal, and you use the standard copy command, and it encounters a locked file, it might just skip it silently. If you use Robocopy /edgev, it generates a verbose output, a highly detailed, itemized receipt showing exactly what files were successfully copied and, crucially, exactly what files were skipped or locked.
Yep.
You instantly generate a complete, legally defensible audit trail of your extraction process. You can prove exactly what you did and what you didn't do.
That audit trail is your shield in court. So you have navigated the boot sequence, you deployed Robocopy, and the critical data is securely resting on your sterilized target drive. The next massive question every investigator faces is, how do we mathematically prove to a judge, a CEO, or a hostile defense attorney that the data we collected is an exact, untampered replica of the original source?
This brings us to the cryptographic core of digital forensics. We're stepping into the digital fingerprint, validation, and the SSD curveball.
Validating evidence is the single most critical aspect of computer forensics. I cannot overstate this. If you cannot validate it mathematically, you cannot use it legally. Validation requires utilizing a cryptographic hashing algorithm utility.
Right. We touched on this earlier.
As we briefly touched on during the compression discussion, these algorithms process the raw binary data of a file and generate a unique hexadecimal or binary string. It is a true mathematically perfect digital fingerprint. If you change a single pixel in an image or add a single space to a text document, the resulting hash value changes completely.
The sources list an evolution of these algorithms, CRC32, MD5, and the SHA family, scaling from SHA-1 all the way up to SHA-512.
Yes. CRC, or cyclic redundancy check, was an early method that translates a file into a localized hex value, but it is prone to high collision rates. MD5, or Message Digest 5, became the industry standard for years to show data hadn't changed during transit. However, as computing power grew, vulnerabilities in MD5 were discovered. Today, the forensic standard relies heavily on the secure hash algorithm family. SHA-1 uses a 160-bit cryptographic key, and SHA-256 uses a massive 256-bit key, providing an astronomically higher level of mathematical certainty.
Let's clarify a vulnerability you just mentioned. What happens if two completely different files, say a picture of a cat and a corporate tax return, somehow manage to generate the exact same hash value when run through the algorithm?
That phenomenon is called a collision. While it is technically and mathematically possible, especially with older, shorter algorithms like MD5, where researchers have artificially forced collisions, the mathematical probability of two naturally occurring files generating the exact same SHA-256 hash is so unfathomably low that collisions are generally of zero concern for standard forensic examinations. The math is simply too vast.
So how do we actually execute these hashes in the field? If you are operating within a Linux environment, which is natively built for this kind of low-level hardware interaction, you have a massive suite of tools.
Linux is incredibly rich in cryptographic functions. You can execute the MD5sum or SHA-SUM utilities directly on suspect disks, specific partitions, or individual files to generate immediate readouts. But the true powerhouse in Linux is the DD command. DD is a low-level utility that performs a true bitstream copy of a file or partition into a raw image format.
Let's dive into the mechanics of that. How does a bitstream copy utilizing DD differ from me just dragging and dropping a folder in Windows?
When you drag and drop a folder in Windows, the operating system looks at the master file table, finds the active files, copies the data of those active files, and writes that data to new available sectors on your target drive. It ignores deleted files, it ignores the empty space, and it fundamentally changes the physical arrangement of the ones and zeros.
Okay, so it rearranges things.
Yes. But when you use the DD command to execute a bitstream copy, it completely ignores the master file table. It physically starts at sector 0 of the hard drive platter and copies every single 1 and 0 exactly as they physically layer on the disk, including all the empty space and all the deleted file fragments, perfectly preserving the spatial geometry of the data.
And if you are imaging a massive 10 terabyte volume, you can pipe the DD command into the split command, which will automatically segment that massive raw file into manageable 2 gigabyte chunks so they fit on smaller target drives. But the open source community didn't stop at DD, did they?
No, the community recognized that DD lacked built-in progress indicators and native hashing. So the Department of Defense Cybercrime Center developed DCF-LTD. This tool was engineered specifically for forensics. It creates the raw binary files just like DD, but it simultaneously hashes the data on the fly and provides a progress bar.
Very helpful.
Very. Then the community took it a step further and created DCT, which is essentially DCF-LTD with vastly improved error reporting features and more robust hashing options.
If you are an IT manager working strictly in a Windows enterprise environment, your native hashing options used to be pretty dismal. You'd had to rely heavily on third-party downloads.
That was true for a long time. But with the introduction of PowerShell version 4.0 and beyond, Windows finally integrated robust cryptographic capabilities. PowerShell now features the semdlet get file hash. It is incredibly powerful. You can generate MD5, SHA-1, SHA-256, SHA-384, and SHA-512 hashes natively right from the Windows command line without installing any outside software.
That's great.
Furthermore, if you need to rapidly compare two files to see if their contents are identical, you can use the Legacy DOS Commands Comp, or FCC. Within PowerShell, you execute compare object, and in Linux, you utilize the diff command, which is phenomenally detailed. I mean, it will output a text file showing you the exact line of code where two seemingly identical text files diverge.
Validation is the bedrock of forensics. But here is where we bring everything all the way back to our opening hook, the ticking clock, the solid-state drive curveball. We have to dive deeply into the physical architecture of why modern SSDs are a forensic investigator's absolute worst nightmare.
To understand the nightmare, you have to understand the hardware evolution. For decades, we relied on magnetic hard disk drives, or HDDs. These drives use a physical spinning magnetic platter and a mechanical read-write arm to record data on physical tracks, very similar to a record player.
Right.
When you delete a file on a magnetic HDD, the operating system does not erase the magnetic signature on the platter. It simply updates the master file table to mark that physical sector as available for new data. The magnetic remnants of your deleted files stay perfectly intact on the platter indefinitely until the computer eventually decides to write a new file directly over that exact physical spot.
And that architectural quirk is why forensic investigators can recover deleted emails from magnetic drives years after they were erased.
Exactly.
But solid-state drives do not have spinning magnetic platters.
They do not. Modern SSDs abandon magnetic storage entirely. They utilize arrays of NAND flash memory chips. These chips store data in microscopic volatile memory cells using electrical charges. And NAND memory physics are vastly more complicated than magnetics. In a magnetic drive, you can write new data directly over old data. In an SSD, to write new data to a NAND memory cell that already contains old deleted data, the SMD must first completely electrically erase the old data to reset the cell to a zero state.
Oh, wow. So it has to clear it first.
Yes. It physically cannot overwrite. It must erase, then write. And the process of electrically erasing memory cells is relatively slow, which degrades the drive's overall write performance.
Yet in the consumer tech market, SSD manufacturers live and die by advertising lightning-fast write speeds. They cannot afford for their drives to slow down because they're busy erasing old cells before writing new ones.
To solve this physics problem and maintain maximum advertised speeds, SSD manufacturers build highly aggressive, automated maintenance utilities directly into the drive's internal hardware controller. These utilities manage the NAND memory chips entirely in the background, independent of the user.
These utilities are wear leveling, garbage collection, and the infamous trim command. Let's break down the mechanics of these utilities, because they are the exact culprits destroying our evidence. Starting with wear leveling.
So flash memory cells have a finite physical lifespan. They literally degrade over time. If an operating system writes and erases data to the exact same memory cell repeatedly, that specific cell will burn out and die very quickly. Wear leveling is an automated internal algorithm that ensures all memory cells across the entire drive get used evenly. It constantly invisibly moves data around in the background so that all cells share the exact same number of read, write, and erase cycles, thereby extending the total physical endurance of the SSD.
Then we have garbage collection.
Garbage collection acts as the drive's internal housekeeper. It continuously spans the memory blocks, maintains a map of memory pages that hold active data, keeps track of which pages are marked as free, and physically moves valid data from fragmented blocks into consolidated new blocks to free up large, continuous chunks of clean space for future fast writing.
And finally, the ultimate nail on the forensic coffin. The trim command.
Trim is the bridging utility that communicates directly between the computer's operating system and the SSD's internal controller. When a user highlights a folder of incriminating financial spreadsheets and hits delete, the OS tells the trim utility, I no longer need this data. Those sectors are logically free. Trim then immediately turns to the hardware's garbage collection utility and issues an aggressive command. Go to those specific memory cell blocks and completely permanently erase them in the background right now. Do not wait. Wipe them clean so they are electrically zeroed out and ready for the next time the user wants to save a file at maximum speed.
This brings us back to the crime scene. If an investigator walks into an office, sees a powered-on laptop with an SSD, and immediately unplugs the power cable from the wall, the hardware loses power, the SSD controller shuts down, and the data is frozen. But if the investigator makes the catastrophic mistake of interacting with the active computer, or if they seize the drive, take it back to the lab, and simply plug it into a power source without a write blocker, the SSD's internal controller powers up.
Yep, it wakes right back up.
The trim function instantly resumes its interrupted background tasks. It actively sweeps through the unallocated space, the exact physical location where the deleted smoking gun spreadsheets reside, and permanently electrically zeroes them out to optimize the drive.
The drive actively destroys its own deleted evidence simply because it was supplied with electricity. The investigator doesn't even have to click a single file. Because the unallocated space is being physically altered by the drive's internal controller, the cryptographic hash value of the entire drive fundamentally changes while you are staring at it.
So what is the mandatory practical takeaway for the IT student listening right now who wants to avoid ruining a federal investigation?
The absolute first protocol upon seizing an SSD, before you even attempt to initialize your imaging software, is to interface with the operating system or utilize your advanced hardware write blocker settings to explicitly disable the trim function and halt the garbage collection routines. You must sever the controller's ability to execute maintenance. Stop the routines immediately to preserve the unallocated data fragments and ensure the drive's cryptographic hash value remains perfectly static during your acquisition.
Let's explore a worst-case scenario. Let's say I'm an investigator. I secure the SSD. I follow protocol. I run a SHA-256 hash on the source drive. I execute my bitstream forensic copy using DCFLTD. I run a SHA-256 hash on my newly minted target image. I look at my terminal screen and my stomach completely drops. The two 256-bit strings do not match.
Nightmare.
The hashes are different. Did I just legally ruin $1 million case? Is the evidence entirely inadmissible?
It is a terrifying moment, but no, you did not automatically ruin the case. A mismatched hash could certainly be caused by an unmitigated trim function, but if you properly controlled for that, a mismatch often simply indicates physical media failure. Remember the concept of MTTF, mean time to failure.
Oh, right. Drives naturally dying.
Exactly. Physical storage drives constantly degrade. It is entirely mathematically possible that a microscopic physical sector on the original source media was critically faulty, and it finally died and became unreadable during the 3 hours it took between you hashing the original drive and your imaging software finishing the copy. Or, as we discussed earlier, you might have experienced a microscopic packet drop due to a thermally degraded SATA cable.
So when you see that mismatch, what is your next professional move?
You never panic. And you never, ever try to hide the mismatch. Transparency is your legal shield. You immediately take the documentation to the primary forensic examiner or the managing legal team, and you analytically explain the variance. You utilize forensic analysis tools to isolate exactly where the hash diverges.
So you track down exactly what broke.
Yes. If you can forensically mathematically prove that the hash mismatch was caused by a documented physically bad sector failing in an area unallocated space, and you can prove that the bad sector was not part of the actual active evidence files required for the trial, the core evidence remains largely sound and legally admissible. A hash mismatch demands rigorous scientific analysis and an expert explanation. It does not automatically negate the evidence if the physics of the hardware failure support your conclusion.
That is a massive release and a great lesson in professional integrity. But hashing and imaging a single standalone solid-state drive is one thing. What happens when the digital footprint you're investigating doesn't belong to a single executive's laptop, but rather belongs to a multinational corporation spanning massive, interconnected server arrays? Let's move to our final major topic, the behemoths, RAID arrays, and commercial tools.
When you transition from consumer-level hardware investigations to enterprise business systems, you inevitably encounter RAID architecture. RAID stands for Redundant Array of Independent Disks. In a RAID configuration, a hardware controller or software utility combines two or more separate physical hard drives into one single massive logical volume.
Originally, RAID was engineered as a hardware redundancy measure to protect critical corporate databases against catastrophic single-drive failure. But it is also heavily utilized to achieve massive, aggregated read-write speed improvements.
Yes. The textbook outlines several specific RAID configurations, and understanding the architecture of each is critical for a successful acquisition. Let's break down the major ones, starting with RAID 0.
Okay, lay it out for us.
RAID 0 is commonly referred to as striping. Imagine a massive video file being broken down into alternating equal-sized chunks. Chunk A is written to disk 1, chunk B is written to disk 2, chunk C is written to disk 1, and so on. It provides incredibly rapid data access and maximizes storage capacity because two physical disks act simultaneously as one large volume, writing in parallel.
But there is a massive glaring disadvantage, right?
There is absolutely zero redundancy. If disk 1 suffers a mechanical failure, the entire RAID 0 array is permanently destroyed because you only possess half of the alternating chunks of every single file.
It is high speed with massive catastrophic risk. Let's look at a hypothetical scenario. Imagine a fast-growing startup that buys a dozen cheap hard drives and links them all in a RAID 0 array because they want lightning-fast access to their massive CAD rendering files. They don't understand the architecture. One single cheap drive burns out, And because there is zero parity, their entire intellectual property database is instantly shredded into useless alternating digital confetti.
And if you are called in to acquire that broken RAID 0 array, you are looking at a nearly impossible data recovery nightmare, not just a forensic acquisition.
Wow. In contrast to that risk, we have RAID 1.
RAID 1 is known as mirroring. It is engineered purely for data recovery and redundancy, sacrificing speed and total storage. Disk 1 and Disk 2 contain exactly identical one-to-one content. Every time the server saves a file, the RAID controller physically writes that file to both disks simultaneously.
Very safe.
Exactly. If Disk 1 explodes, Disk 2 is an immediate, perfect, bootable replica. From an acquisition standpoint, imaging a RAID 1 array is essentially identical to imaging a single drive.
Then the architecture scales up to RAID 2 and RAID 3.
RAID 2 operates similarly to RAID 1 mirroring, but the data is striped and mirrored at the microscopic bit level rather than the block level, which provides highly aggressive, real-time data integrity checking using Hamming codes. RAID 3 introduces a new concept. It utilizes data striping across multiple active disks for speed, much like RAID 0, but it integrates a dedicated separate parity disk.
Parity is a complex mathematical calculation, right? An XOR logic gate.
Yes, that allows the RAID controller to mathematically deduce and rebuild lost data if one of the primary storage drives fails. RAID 3 requires a minimum of 3 physical disks to function.
But if you walk into a Fortune 500 data center, the heavy-hitting architecture you are almost guaranteed to encounter is RAID 5.
Exactly. RAID 5 is the enterprise standard. It utilizes block-level striping across multiple drives for excellent speed, but instead of relying on a single, vulnerable, dedicated parity disk like RAID 3, RAID 5 distributes the mathematical parity recovery data evenly across every single disk in the entire array.
Let's explain the business impact of distributed parity. If a business is running a massive RAID 5 database and drive number 4 completely catches fire and dies, the server does not go down. The IT manager can walk into the server room, physically pull the melted drive out of the rack, slide a completely blank brand new drive into the slot, and the RAID controller uses the distributed parity math from all the surviving drives to automatically recalculate and rebuild all the missing data onto the new drive, all while the server remains perfectly online and operational for the company.
It is an incredibly resilient architecture, but if you are a forensic investigator, the prospect of executing an acquisition on a massive RAID 5 array is sheer terror.
Why is it so terrifying?
It comes down to sheer physical size. Modern enterprise RAID systems are no longer measured in gigabytes. They are pushing deep into terabytes, petabytes, and in some massive cloud infrastructures, zettabytes of data.
Wait, let's play this out. If a financial corporation is running a 200 terabyte RAID array, and I want to follow the gold standard and execute a static, physical disk-to-image bitstream acquisition, I would physically need 200 terabytes of blank, sterilized target drives loaded in my van just to hold the raw image.
Yes, you would need a staggering amount of hardware just to hold the image, and more critically, you would need the physical time to transfer 200 terabytes over a data cable, which could literally take months of continuous transferring. This is exactly why a static, physical bitstream acquisition of a massive enterprise RAID array is practically impossible, and frankly, of absolutely no targeted use for a specific legal investigation.
So what is the tactical approach when facing a behemoth?
This is the exact scenario where you are forced to abandon the physical image and rely entirely on logical or sparse acquisitions. If you are investigating a CEO for embezzlement, you do not need to acquire the 150 terabytes of encrypted marketing video assets stored on the RAID. You only need the specific Exchange email server files and the localized financial databases.
Right, you legally scope your search warrant and you extract only the data relevant to the investigation.
Exactly. Furthermore, you have to verify that your specific forensic analysis software is mathematically capable of reading a forensically copied RAID image because the data is striped across multiple disks. The software has to know how to digitally reconstruct the RAID array virtually in order to make the extracted files readable.
To handle these massive, complex network architectures and failing hardware, investigators cannot rely on free, open-source command line tools. They rely on heavy-duty, highly specialized commercial tools. The textbook provides a list of tools you might encounter, but I want to focus deeply on 2 specific scenarios where these commercial tools save the day.
Okay, the first scenario involves physically failing hardware. If you are dealing with a hard drive that has suffered severe platter damage, standard imaging tools will often hit a physically bad sector, lock up, and completely crash the acquisition process. In this scenario, investigators turn to ASR data SMART. SMART is a highly robust Linux forensics analysis tool engineered specifically with advanced data reading capabilities for degraded hardware.
That's incredible.
It really is. It is programmed to intelligently power through physically bad sectors, selectively ignoring the catastrophic read errors that freeze other software, allowing it to successfully extract the surviving image from a dying drive before the mechanical arm snaps entirely.
The second scenario is the geographic nightmare. Imagine you are a forensic IT consultant hired by a multinational bank. The suspect computer is an active server sitting in a highly restricted Level 4 secure data center halfway across the country. You're legally forbidden from physically entering the server room, and you certainly cannot carry a laptop out of the building. How do you acquire the data? This is where X-Way's Imager becomes a lifesaver.
X-Way's Imager is engineered for modern distributed corporate environments. It possesses the capability to quickly and securely acquire data from a remote network-connected computer. You can deploy the software remotely, establish a secure encrypted tunnel to the suspect server, and mathematically clone the specific logical drives over the network directly back to your secure lab. You never have to physically touch the restricted server rack.
You pair a powerful remote capability like X-Way's Imager with the deep architectural understanding of how RAID parity mathematically rebuilds data, and you possess the foundational skills to tackle almost any massive enterprise acquisition.
It is a phenomenal skill set that makes you an invaluable asset to any corporate IT or legal department.
We've covered a truly massive amount of technical and operational ground today. Let's pull all of these complex concepts together and distill the core recap. What is the ultimate takeaway for the business student? Data acquisition is not the casual act of plugging in a thumb drive and hitting copy. It is a highly structured, scientifically rigorous methodology. It requires a constant, calculated balancing act between the physical speed limits of your hardware, the massive financial constraints of enterprise storage budgets, and the absolute unforgiving necessity of mathematical forensic integrity.
Whether you are meticulously extracting data from a single consumer-grade flash drive found in a company parking lot, or you are executing a targeted logical extraction on a 200-terabyte RAID 5 server in a corporate basement, the fundamental guiding principle of digital forensics remains exactly the same. Analyze the copy, strictly preserve the original.
And that core principle brings us right back to our opening hook. That invisible ticking clock of the solid-state drive's automated trim function, slowly and methodically permanently erasing the deleted evidence in the background. That ticking clock is exactly why we formulate exhaustive action plans. It is why we utilize highly specialized RAM-based operating environments like Kali Linux or Mini WinFE to forcefully mount suspect drives strictly as read-only.
Exactly.
It is why we deploy hardware write blockers to sever the communication cables, and it is why we always, without exception, validate our target images with complex cryptographic hashes like SHA-2556. We have to beat the physics of the clock without mathematically breaking the evidence.
It is an incredibly high-stakes environment where one missed protocol can ruin a multi-million-dollar case. But with the right theoretical foundation and meticulous preparation, it is an entirely manageable and deeply rewarding field.
And to you, our listener, the driven Tarleton State University business and tech student, thank you for joining us on this extensive deep dive. If you found these highly technical insights valuable for your future career trajectory, please hit that like button, subscribe to the feed, and share this audio with your classmates. The more IT professionals who truly understand the physical mechanics of data preservation, the more secure our global enterprise systems will become. Be sure to check the description below. We've linked some incredible in-depth additional resources and white papers you'll definitely want to explore to continue your education and stay ahead of the technological curve.
Seizing control of your career means continuously seeking out complex knowledge and relentlessly leveling up your practical skills.
Next week, we are moving forward into Chapter 5. We are stepping away from the microscopic ones and zeros of the data itself, and we are zooming out to look at the physical, macro environment surrounding the hardware in processing crime and incident scenes. It is going to be a fascinating look at the physical logistics of an investigation. In the meantime, I highly encourage you to review our channel for other focused playlists, deep dive videos, and lectures.
As we conclude this session, I want to leave you with a final forward-looking architectural thought to mull over. We've discussed how incredibly massive enterprise data is becoming, and how difficult it is to freeze a live environment. As corporate storage arrays inevitably push past petabytes and deep into the zettabytes, and as advanced AI systems begin to dynamically optimize data deletion and garbage collection in real time across decentralized cloud servers, How will the legal and technical definition of a complete forensic acquisition have to evolve in the next 5 years? Will we ever again be able to physically capture everything, or will the entire digital forensics industry be forced to mathematically redefine what constitutes admissible evidence?
That's a wrap on this episode of Digital Forensics. Until next time, analyze the copy, preserve the original.